In this video, we're going to look at estimation methods in HLM and then talk about how we can test fixed effects. As a quick note, the R2 MLM package was released on the Grand Network this week. Would have been nice if it was there last week, but it is now. I would recommend upgrading or updating to the official version. I haven't noticed any differences yet, but it can't hurt. Getting started this week, we're going to look at the pane data again. So I'm getting set up by loading up LME4, loading up my data. And first, we're going to talk about the difference between restricted and full maximum likelihood. You can fit models using either method in LME4. The default is RAML equals true. So if you want restricted, you can ignore that line. I'm just showing you that it's there. And if you want full, you set it to false. And that will give you full maximum likelihood. Now, take a second and see if you can remind yourself as to what the difference is before we go ahead and take a look. And so when we look at the actual differences in our estimates, note that the parameter estimates for the fixed effects are almost identical. The only reason they're slightly different is because of the way the algorithm works. It can have a little bit of slight differences each time you refit a model, but here it's in the 4th decimal, so we're not too concerned about it. And then also note that the standard error is where we actually see more meaningful differences. The standard errors in the restricted version are a little bit larger than in the full version. So here you see the standard error up here is 1.08. Down here it's 1.06. Not a huge difference, but a more meaningful difference. We will also see differences in the parameter estimates for the variance parameters or the random effects. So you see the variance of the cluster means is quite a bit larger in the restricted maximum likelihood version than in the full maximum likelihood version. The reason for this is that full maximum likelihood is essentially treating your model as if it included all of the population data. There's no penalty for sample size in full maximum likelihood, whereas in restricted maximum likelihood, we do have a penalty for sample size. So restricted maximum likelihood is going to be a little bit less biased in small samples, whereas full maximum likelihood is going to be susceptible to small sample bias. As a result, we want to use restricted maximum likelihood in almost every case. There is one exception, and that is when we're using the likelihood ratio test for fixed effects, which we will talk about shortly. Before we do that, we're going to go back in time a bit and talk about some of the fundamental ideas of inference testing in statistics by talking about z-tests. Z-tests are tests that tell us how many standard errors a parameter estimate is from 0 by dividing the parameter estimate by the number of standard error, by its standard error. So for example, if our parameter here is theta hat, which is an estimate of just some ambiguous parameter, it could be anything. It could be a gamma, it could be any parameter that's normally distributed, it could be a beta. So if our parameter estimate is exactly the same as the standard error, that means that it is one standard deviation away from 0. If it's twice as large as the standard error, it means it's 2 standard deviations away from 0. And this is in the sampling distribution of the parameter. So what this means is that if you recall in a normal distribution, including a sampling distribution, 96% of observations fall within 2 standard deviations of the mean, and 95% of observations fall within 1.96 standard deviations of the mean. And this is important because what this tells us is that if the absolute value of z is greater than 1.96, that under the null hypothesis, under the null sampling distribution, it means that there is a 5% chance that we would have observed a parameter value this large, or with an absolute value this large or larger. And z-tests are unbiased in sample sizes as they approach infinity. So in very large samples, z-tests are fairly reasonable to use, but in smaller samples, they are not. They will be biased and give you incorrect inferences for your z values. So the reason this is all important is because when we're using LME4's Elmer function, it tells us it's giving us a t value, but it's really giving us z's. So this t value is the same thing as a z value. It's or a z-score. It's the parameter estimate divided by the standard error. So this value is this value divided by this value. And so if we're going to use z-tests, we can look at these values and essentially we can think about which ones are significantly different from 0 if we assume this was an infinite sample size by saying which of these t's is greater than, or the absolute value of which is greater than 1.96. So here the intercept is significantly different from 0 and the active variable is significantly different from 0. But these two, because they are within 1.96 standard errors from 0, they are not significantly different from 0. The other thing that we can do with LME4 is jointly test multiple parameters at the same time, or multiple fixed parameters at the same time. And we do this using the likelihood ratio test. As we've discussed previously, the likelihood ratio test follows a chi-square distribution. We do this with the little a ANOVA function, where we can compare two nested models, one a restricted version with fewer parameters compared to a full version. And when you do this, as mentioned before, we need to use full maximum likelihood rather than restricted maximum likelihood. Otherwise, the likelihood ratio estimate will not be correct. And the little a ANOVA function will do this for you, but it's still important to remember that this is a full maximum likelihood model test, and so it's also susceptible to small sample bias. And so you see what I do here is I fit a reduced model where I've taken out the number of diagnosis variable and the chronic pain variable and just have the active variable. And then I test my original model with all three variables compared to the model with just one variable. And this will test whether these two extra variables, chronic pain and number of diagnoses, significantly predict p affect above and beyond the active variable. And here we see we get a chi-square value of 3.44. Degrees of freedom 2 is not significant with p 0.018. So now changing gears back to z-tests and t-tests again, you might be wondering, so where are the degrees of freedom? Why can't we use a t-test? And just as another sort of conceptual review, the difference between a t-distribution and a normal distribution is that a t-distribution is parameterized by degrees of freedom rather than by variance. So a normal distribution is parameterized by its mean and variance. A t-distribution is instead parameterized by its degrees of freedom, and we usually think of a t-distribution as having a mean of 0. So t-tests tell us the location on the t-distribution of a parameter value that is t standard errors from 0. So the t statistic is the same as the z statistic. It's just that we're looking at a slightly different distribution on which we're placing our parameter. We're saying that it's the actual number of standard errors is the same, but the distribution on which we're computing the probability is different. It's a t distribution parameterized by degrees of freedom rather than a normal distribution parameterized by standard deviations or variances. So this allows us to then compute a probability that under the null hypothesis, we would observe a parameter estimate at least as extreme as the one we have. And this is straightforward to do in a single level model where we can calculate degrees of freedom simply by taking the number of observations and subtracting the number of parameters. But it turns out this degrees of freedom is too large for appropriate estimates, or more precisely, appropriate type 1 error rates in HLM. We'll get inflated type 1 error rates if we use these degrees of freedom. So there are two well-established methods for estimating degrees of freedom in HLM, the Sater-Waite method and the Kenward-Roger method. And these are estimates of degrees of freedom because they're not integers, and conceptually degrees of freedom have to be integer values. What these methods are doing is they are estimating what the degrees of freedom should be to preserve appropriate type 1 error rates. We can get these degrees of freedom estimates with the Elmer test package, and it implements both of them. And it does this by actually overwriting the Elmer function. So once you load Elmer test, that gives you a slightly different version of the Elmer function that includes the degrees of freedom methods. So I usually hide these warnings in these slides, but here I'm showing you what happens when I load Elmer test. what should happen when you load it is we get this message that says we're attaching the Elmer test package and that we're masking an object from LME4, and this object is Elmer, which is obviously a function that we're using all the time. So what this means is the LME4 version of Elmer has been overwritten by Elmer test, and you can avoid this by directly accessing functions from certain packages by naming the package, putting a double colon, and then the function. So if you wanted to run the Elmer test, Elmer, without loading it, you could call Elmer test double colon Elmer. And you could also do the same thing if you've loaded both, but you want to get the LME4 version back by calling LME4 double colon Elmer. And you don't even need to load any of these packages to do any of this. You just need them installed. This is an alternate way of accessing an installed package without necessarily loading it, but it'll still work if the package is loaded as well. So now that we've discussed what's going on here with the Elmer function and the two different packages, we can refit our model with the Elmer test version. And now when we check the summary, we get degrees of freedom. And note that these are not integers, they have decimals, so again, they're degrees of freedom estimates, but they do allow us to now parameterize our t value, our t distribution in such a way that we can compare our t value to its location in the t distribution and get correct p values. We can also get the Kenwood-Roger degrees of freedom. This is just calling the DDF equals Kenwood-Roger. The default is Saderweight. The biggest difference is that the Kenwood-Roger version takes quite a while to run in R. It took 17, 18 seconds in my version here, whereas the Saderweight version is almost instantaneous. So I tend to use the Saderweight version just for efficiency purposes. There isn't really a big difference between the two. That's well known. Either one should work. So the last thing to talk about is that we can also do multi-parameter tests using these degrees of freedom adjustments. And we have to do this in a slightly more complicated way in the Elmer test package. And we do this with a contrast matrix and then use the contrast MD function. And so the way the contrast matrix should work is that it should have the number of columns equal to the total number of fixed effects in your model, including the intercept. So it's the number of predictors plus 1. And then it should have rows equal to the number of fixed effects you want to simultaneously test. And then each row should be all zeros except for in the column that matches the associated parameter of interest in the order that it was entered into the model formula, plus 1. Remember, you've always got to add 1 for the intercept. So, for example, if we wanted to test the simultaneous effect of number of diagnoses and chronic pain, as we did before with the likelihood ratio test, we want a 2x4 contrast matrix. The first row gets a 1 in the column matching where n diagnose is entered into the formula, and the second row gets a 1 where chronic pain was entered into the formula. So here's an example of how you could do this. And when you looked at this in lecture, Dr. Cham entered this part directly into the contest MD function. I'm doing it as a separate object just to show you what it looks like. So here, what this rbind is doing is it's binding these two rows together into a matrix. So it's saying this is one row of matrix, this is a second row of matrix. Let's smush them together, and it gives you this, which is what I described before. So the first row has a 1 in the second column, and that's because the parameter of number of diagnoses was entered as the first parameter in our formula, so it's the intercept plus 1, and chronic pain was the second parameter, so intercept plus 2. So remember, this first column is for the intercept. It should always be all zeros. So here we have number of diagnoses and chronic pain, and then the last parameter we want to leave in our model is active, so that gets all zeros. And that gives us a multi-parameter test. This is actually an F test. An F test is equivalent in concept to a t-test in some ways. You talked about that a little bit in lecture, except the F test can have more than one parameter at the same time. So here we get an F test with the Saderweight degrees of freedom. Here we have the Kenwood-Roger degrees of freedom. Now, this is a headache to code. you can imagine if you have more complicated models, lots of predictors, having to write out that whole matrix. I mean, imagine if you had 8 predictors and you had to write out a matrix with 8 columns and then a row for each predictor you wanted to test. That would be a pain. So I coded up a present for you. This is a function that will do this automatically for you. And this, I don't, I'm sure that this exists somewhere or something like it exists in a package somewhere. I couldn't find it. I tried pretty hard, but I couldn't find it. So what this is doing is it's taking your specifications and it's automatically generating a contrast matrix for you and then testing your parameters. I won't go into the details of exactly what this function is doing, but this is an example of how you can write a custom function in R. You call what you do is you name it and then you set it to function. And then in the parentheses, you are naming what gets entered into the function. So here I'm saying I want 3 arguments to my function, which I'll talk about in a second. And then in the curly brackets, you put exactly what you want your function to do. And so what this function will do is it takes 3 arguments, mod, which is an Elmer model that you want to do a multi-parameter test on. Pars is the parameters that you want to test, and if you leave this to the default, which is all, or you write all, it will simultaneously test all parameters, which is an omnibus test. Or you can change it to any named set of parameters within your model. And then you can change the degrees of freedom. I set the default to Sator weight, but you can change this to Ken or Roger. And if you then call this, you see you get your multi-parameter test. And so you do have to copy this code and run it. And then once you do that, you will have this function available to you in R. So enjoy.